This particular chapter is, the longest one. We are doing ray optics, and that is the third lecture. In the previous two lectures, we are done with the reflection of mirror, and in the last lecture, we are done with the TIR, real depth, or you can say refraction. In this particular lecture, we are going to talk about the refraction at spherical surfaces by lens, or what is a lens, how many types of lens, power of a lens. And I'm not going to give you the formula of a lens, or you can say lens maker formula is not derived because it is, I think, omitted from CBSE itself. But how we can achieve that, how we can get that particular relation, so we can do that in that particular lecture also. Is this clear, everyone? So that is going to be the important one, because after that we are going to discuss the prism, or you can say we are going to discuss the refraction in the prism, and different you can say subtopics related to that, like scattering or dispersive power and so many things. And then in the next last lecture of that particular chapter, we are going to talk about the optical instrument, telescope, microscope in general, and types of telescope and microscope. Is this clear? So as we already done this particular thing, that is going to be reflection, or you can say a recall. What is refraction of light? Refraction of light is just simple bending of light, or you can say whenever a medium is going to be changed, so the light ray is going to bend from one medium to another medium. So as you can see here as well, this is your incident ray, and that is the incident ray is going to bend a little bit. So this particular bending, if it is not going to be, so what is the scenario is going to be happen? The scenario is going to be the light ray is going to tilt it in this. I mean, the light ray is needed to be passed a straight line in a straight line in this. So this particular band, this particular shift is because of refraction. Is this clear, everyone? In the same way, we have incidence or angle. You can say angle made by the incident ray, or normal, or we have a same angle of refraction R as well, angle made by the refracted. Why it is going to be? Because the medium is going to be changed. It is your medium 1. Medium 1, in general, we have a air or vacuum. Okay. Medium 2 can be anything, water, glass, any particular kind of liquid, and so and so. So that is the general thing. Is this clear, everyone? Moving ahead, what is refractive index? That we also done in the previous class in a great detail. So the refractive index, also called the index of refraction, enable us to know how fast light travels through the material medium. And basically that is the ratio of speed of light from air, or you can say from one medium to another medium. Because in this particular case, or you can say normally we say that refractive index of any particular medium with respect to air. In general, what we assume, in general, what we say and feel, if it is a glass slab, okay, and it is a medium 2, so what is going to be, this is my normal. So for this particular normal, if this is the incident ray, going to be, so the refracted ray is going to be a little, bit tilt. Clear? So obviously what is going to be here, this is your glass medium 2, here the speed of light is V, here the speed of light is C. It is a medium 1, or you can say air, okay, and it is medium 2, or you can say glass in this. So basically the ratio of speed of light in one medium to the another medium. One medium, what particular one medium we take, from which medium is going to be light entered. So that is known as your first medium. That is your angle of refraction. That is angle of incidence. That is angle of refraction. Okay, so that is your N, refractive index, Ri, important one. So you can write it in this way. Clear, everyone? Where C is the speed of light and V is the speed of light in medium. The given velocities of light in different media can be the refractive indices by the wave. N21 means refractive index of medium 2 with respect to medium 1, when we can say that instead of this, if it is going to be, suppose there is a glass, okay, or in this particular glass slab there is a water. I fill the water here. So now we have a two medium all together. So the scenario is going to be same. Okay, now you can see there is a, if there is a normal over there. So how are you going to see this particular effect? This is your incident ray. Okay, this one is the incident ray, and this one is the refracted ray. Now here, the moment it is going to interacted with the water, so obviously there is a medium 2. Now it is going to be more. Okay, because water is going to be lesser as compared to the denser or this particular thing. It is going to be away. Why so? Because the refractive index of water is lesser than the this particular glass. Glass have a 1.5 or water has a 1.33. So what the meaning I am going to share with you, or why I drawing this? Because the moment light enters from this is your R, and that becomes I also for medium 2. You can say I2, R2. Okay. So the moment, I mean, what is the meaning of drawing this? The moment light enters from air to glass, then it is going to be a deviate, or then it is going to be a bend little bit. When again it is going to be enter from glass to water, so then it is going to be the same thing. So here we have a speed of light v1, here we have a speed of light v2, and here we have a speed of light c, which is the speed of light in air or vacuum. So the given velocities of light in different media can given the refractive index by the following, where n21 is the refractive index of 2 with respect to 1. Okay, and n21 is speed of light in medium 1 to the speed of light in medium 2. So basically, that's sometimes written over this also, mu21 v2 v1 upon v2 equals to n21. The meaning of saying that, you can see in both the cases, in equation A or in equation B, we are going to put the velocity of light in a medium of light which is going to be refracted, or you can say the second medium speed of light is going to be in the denominator. Here always it is going from air to glass, so the speed of light in air is going to be at the numerator, and the speed of light in the glass is going to be denominator. Here it is going from glass to this water, so either you can write v1 v2, or either you can write vg, velocity of light in glass, velocity of light in water. Is this clear? So the two important things you can whenever or wherever the refractive index you need to find, so you need to put the velocity of light in the going medium, in the you can say in the second medium, in the denominator. Clear? In the denominator we are going to put the velocity of light into the medium which is going to give you the refraction, or into the second medium itself, whatever the second medium itself, without a doubt. Clear? And in a written sense, this n21 is the refractive index of 2. Obviously refractive index of medium 2, because medium 1 is this glass medium and medium 2 is this water medium. So we are finding how much the light is going to be bent whenever it is going to enter in medium 2. So the meaning of saying that, we are need to put the velocity of light in medium 2 into the denominator. Then we are going to able to find it out. Is this clear, everyone? Shushita, Sai, and this Yajira, beta, please open your cameras. Okay. So now Snell's law, we done this thing in a great detail. So that is the recall Snell's law. What is that? That is, you can say, second law of refraction also. Second law of refraction states that the sine of angle of I, or incidence, to the sine of angle of refraction is a constant thing, and or sine of angle of incidence divided by sine of angle of refraction is v1 by v2 equals to n2 by n1. It is going to be for air to any particular medium, for air to any other medium, any other medium means one medium is going to be air here, air here. Wow, what a rhyme. And here for medium 1 to medium 2 other than air, medium 2 other than air. Okay, other than A. So I and R the angle of incident and refraction, N is the refractive index, and N1 and N2 are the refractive indexes of the medium 1 and medium 2. V1 and V2 are the speed of light in medium 1 and medium 2 respectively. Clear everyone? So that is already done. I'm just giving you the you can say glance what we already done. Now this is the important thing, and from this particular slide we are going to learn the new thing. Clear? Clear na? So yeah, this okay, wait a minute. This image I need to paste on each particular page first of all, so you can get a better quality to understanding. Just a minute. Okay, so as you can see, we are going to just find the refraction at a spherical surfaces, and from this particular one spherical surfaces, if I add the same spherical surfaces in this way, so I make a lens. Clear? But right now I am not going to give you this. I am just wanted to give you a relation or a formula whenever any particular you can say object is in the front of spherical surface instead of glass, because in simple glass we learn this particular concept in class 10. Whenever a ray of light is entered in a glass slab, so that is going to be tilted a little bit. Okay, and then we also find the lateral shift D, or you can say real depth or apparent depth in the previous lecture, and the shift in between the real depth and the apparent depth, right? So in this particular lecture what we are going to find, instead of a single you can say instead of this particular glass slab simple or flat surface, if we have a this particular kind of tilted surface, or you can say spherical surface, so what is going to be the scenario? So consider two transparent media having indices of medium 1 and medium 2. So you can see that is here medium 1 and medium 2 and mu1 and mu2. That is going to be mu1 and mu2. Refractive index in general. Mu1 and mu2. Where the boundary between the two media is spherical surface of radius r. This particular spherical surface have a radius r. We assume that again this mu1 is lesser than mu2. It is going to be because the another medium we take here, the glass, and glass have a refractive index mu2 higher than the refractive index of air, because mu2 refractive index of glass, refractive index of glass, refractive index of glass is going to be 1.5. Okay, and which is mu1 for air is going to be 1. Clear? Let us consider a single ray leaving point O. Right now we are just finding this, focusing at point I. Okay, so what is going to be here? Image is going to be created at this particular point I, and object is situated at this particular point. So applying, or you can say Snell's law applied to this refracted surface gives. So till now just we are giving the naming and everything. Nothing new we are doing here. Clear? Suppose there is an object O is situated at this O, and the image you get this. How it is going to be? There is a normal. So one ray is going to be in this way, so it is going to be refracted. As simple as that. Clear bit everyone? Clear na? Since next page we are going to do the little bit geometry or mathematics, nothing more than that. So according to the Snell's law, as we know, Snell's law what it states that sin I divided by sin R is mu2 by mu1. Instead of IR, what can do that? Because that is your incidence angle or incident ray. So making an angle, or you can say incidence angle theta 1, and with the refraction that is going to be theta 2. So here angle of incidence is theta 1, or angle of R, or angle of refraction R is theta. Clear everyone? And this one is also theta 1, theta 2. This one is also because theta 1 and theta 2 are measured to be small. We can use the angle of approximation. Means as we can see, when theta 1 and theta 2 are the small, so using angle approximation, what is the meaning of this? Sin theta is going to be theta for theta greater than 1 degree, lesser than 5 to 10 degree. In between this range, we can put sine theta equals to theta. Is this clear? Clear? Because if we doing so, meaning of saying that if we are doing this particular thing, so okay, first of all, this is a right angle triangle. In a right angle triangle, we have a sine theta component, right? And what is a sine theta? Sine theta is P by H, perpendicular hypotenuse. Clear? This is your sine theta, na? Theta, our sine theta is P upon H. Sine theta equals to P by H. Okay. Now what I'm saying, if this theta is very less, so you can see that P and H is going to be almost same. Clear? And for this kind of scenario, when it is going to be almost same, so then theta is going to be, sine theta is going to be converted into theta only. Degree, how much the angle it is. Clear? So that is the relation here. So angles in radians, and say that, so from this particular relation, which is, you can write it down, this relation number 1, that is, this is your relation number 1, equation number 1, like mu1 sine theta equals to mu2 sine theta, and from where it comes? From this particular terminology. Sine theta 1 equals to sine theta 2. Clear? From this thing it is going to be. So then mu1 equals to theta 1 and mu2 equals to theta 2 we have. Clear beta? This one? Good. So now moving ahead. Okay. I can paste this one to make it visualized again what is going on there. So let me paste it down first, and then we are going to. So just a minute. Okay, as you can see, this is necessary to draw here. From the geometry, what is the geometry means? As we know, there is a identity. The exterior angle of a triangle is equal to the sum of opposite two angle in a triangle. Clear identity. This equation 1, or you can say what this equation 2 arises from. Okay, let me write it down here. Equation 2 comes from an identity. And that particular identity is in 10th class. Comes from an identity in the geometry. Identity from geometry. Okay. From geometry. What it is? Exterior angle of a triangle. Exterior angle of a triangle equals to sum of two opposite angles in a triangle. Angle in the triangle, or you can say inside the triangle. Okay, clear? So from this particular identity, from this particular identity, what we can get then, as you can see here, theta 1. Okay, first of all, these are the two angles in a triangle. That is my alpha. This is the alpha, and that is beta. This one is beta. So this is your theta 1, which is the exterior angle. Clear? In triangle OPC. In triangle OPC, the exterior angle is theta. Angle. And this alpha beta, here I can write alpha or beta are interior angles. Interior angles. this clear? So from this particular identity, this equation we can write it down. Is this clear, everyone? Okay. So then after that, that is very easy. We are not going to do much about it. Then beta equals to theta plus alpha, theta 2 plus gamma, same again. This beta 2 is the exterior angle and the theta 2 and gamma is the interior angle. Clear na? Now triangle CPI. This is, okay, I can write for triangle CPI. You can find it down. And this one for triangle OPC. Clear? So this equation number 2 for triangle OPC and the equation number 3 is for triangle CPI. Now equation 1 and 3 can be combined to express theta 2 in terms of alpha and beta. Substituting what we are doing here, the first equation is this: mu1 theta 1 equals to mu2 theta 2. Okay, and we can write on this page also. So mu1 theta 1 equals mu1 theta 1 equals to mu2 theta 2. So this is my equation number 1. So theta 2 I can write beta minus alpha, and substituting this in terms of alpha we will get this. Okay, is this clear? I am not writing that particular step. First of all, theta 2 you can put here in the equation 1, which is mu1 theta 1, and mu theta 2 you can put beta minus gamma, and then this theta 1 theta 2, or and the value of theta 1 we can put, I mean just put the value of theta 1 and theta 2 in this equation 1. You can understood in this way also. Clear? With the help of equation number 1, 2 or 3, you can see that with the help of equation 1, 2 and 3, put the value of theta 1 and theta 2 in equation 1, where theta 2 you can write, or you can say equation number this 3 can be rewritten as, equation number 3 can be rewritten as theta 2 is beta minus gamma. So from this equation, when we put the values of theta 1 and theta 2 in equation this 1, so we can get this. Clear? And you can write this is your equation number 4. Now moving ahead, we know this sine mu1 alpha plus mu2 gamma equals to going to be mu2 minus mu1 beta. Since the arc PM of length S subtends an angle beta at the center of curvature, so beta equals to S by R. Again this require this. Okay, wait a minute. S by R. I need this diagram in it. Wait. Just a minute. Theta 1, theta 2. So this equation number 4, what I write, you can see that mu1 alpha plus mu2 gamma is going to be mu2 minus mu1 beta. In teaching geometry, I always failed myself at first hand. So I can put it down here. Give me a minute, beta. Just a minute. That is it. So this mu1 alpha plus mu2 gamma equals to mu2 minus mu1 beta we can get from this equation number 4, or from this equation. Okay, or I can write equation A. From equation A, if we are going to find it down, so mu2 beta, mu1 alpha minus beta plus gamma. So simply we can get this equation. Is this clear, everyone? The equation number 4 comes from equation number 2. Equation 4 we get from equation B. What I write, B or A? A. Okay. Now moving ahead. So this we get mu1 alpha plus mu2 gamma equals to mu2 minus mu1 beta. Or simply you can solve it out here, as you can see that mu2 beta equals to mu1 alpha plus mu1 beta plus mu2 gamma. Clear? And when we are doing this beta beta one side, so mu2 minus mu1 beta equals to mu1 alpha plus mu2 gamma. I think we have the same equation. Clear na? Mu1 alpha plus mu2 gamma. Just rearranging the term, the right hand side is written over left hand side and the left hand side is written over right hand side on the next page. Nothing we change. Now the main thing is arc PM. This arc PM, because this is the arc. Okay, this arc PM is taken as this distance D of length S subtends an angle beta. Okay, suppose we have an arc of this PM of length S subtends at an angle beta at the center of curvature. So this angle, this arc of length having beta at the center of curvature, because this is center of curvature. So beta can be S by R. Why S by R? Because if it is the center of curvature, and we know this again, tan of beta is perpendicular upon base, okay, which is perpendicular this, this perpendicular distance we take as a perpendicular, which is S, and base is simply R. Why can I take R directly? Because the distance from the pole at the center is radius of curvature. Clear na? Is this clear, beta? And from this perpendicular base I can get, as you can see, if it is very small, so this curve I can take as a this straight line which is at S, and this is this line and this is this line. So beta is here, I can get simply here the angle beta is, I can do the tan beta, or tan beta is perpendicular upon base. And for small angle, again for small angle approximation, that is one theorem also, for a small angle approximation, small angle approximation, tan, okay, tan beta is going to be beta. Why so? Because sine theta is going to be theta, and when cos theta is going to be 1. Why so? Cos theta is going to be 1, because cos 0 is 1. So if theta is lesser than 5 degree, we can take it as a 0 degree. Is this clear, everyone? So in this way we can put tan beta equals to beta simply, which is perpendicular upon base. This P is this P is different and this beta is different. Beta is the angle here, perpendicular is the perpendicular. Perpendicular is the arc, or you can say length of arc S, and base here is radius of curvature, because this is the base of yours. This is the base, radius of curvature, and that is perpendicular. Clear, everyone? Is this clear na? So as you can see, in the same sense, also in the paraxial approximation, in the same approximation, this alpha is again a tan alpha, which is this perpendicular upon this base. This is the perpendicular and this is the base. Clear? So that is alpha is S by mu, and gamma, this gamma is S by V, because from this particular point M, this is the V, as we can written directly, and this is the U. U is object distance, V is image distance. Is this clear or not? First of all, tell me this. Is this clear, everyone? So just we are putting here the value of alpha, gamma and beta in equation 4. using these terms in equation 4 with the proper sign. Why we are right now using equation 4 with a proper sign? Again, because in the sign convention in the last lecture, we learn is a great detail pole or this particular point where the refraction is going to be, we take it as a 0. So everything on the right hand side is taken as a positive. Everything on the upper side or in the vertical upward is going to be taken as positive. Everything on the left hand side is taken as a negative. Everything on the downward side is taken as a negative. Clear this thing? So as we can directly see that object is on the left hand side. So it is taken as negative of, u. And image is at the positive side, so we can take as a positive v. Clear? In the same sense, radius of curvature is also in the positive side, so we can take r is positive. R is positive, image distance is positive, object distance is negative. So just putting, I mean, S we can taken out in alpha, beta and gamma, and Kn we can cancel. So this is your one famous relation. Mu1 upon minus u plus mu2 upon v equals to mu2 minus mu1 by r. Or in great detail, how we can write it down? This is mu2 upon v minus mu1 upon u equals to mu2 minus mu1 upon r. Now this is your famous relation, and with this relation we can find out 2-3 things all together. So tell me, is this clear to you guys or not? Till now, because after that everything is going to be in the proper format of optics. Till now we are learning the geometry. Clear everyone? Okay, rewrite and re-revise this thing from the beginning, what we've done. So first of all, refraction at the spherical surfaces, we just take the, we just make the naming, like mu1 is the refractive index of air, mu2 is the, mu1 is the refractive index of air, mu2 is the refractive index of medium 2. You can say medium 1 or medium 2 also. Clear? Where mu1 is less than mu2 is, you can say higher. And taking Snell's law help, we can write it down this thing. mu1 sin theta equals to mu2 sin theta. How? Because sin I by sin r equals to mu2 by mu1. And here angle of incidence is theta 1 and angle of reflection is theta 2. Now using small angle approximation, this particular thing, using small angle approximation, sin theta can be theta. I can write it down here. Tan theta can be write it down theta also, or cos theta is going to be 1. Why so? Because cos 0 degree, because cos 0 degree is 1. Clear? Clear till now? So when we do this, sin theta tends to be theta. So equation 1, or you can say this instead of 1, because I write it down the previous one. This Snell's law, equation A on this page, converted into the equation 1, that is mu1 theta 1, mu2 theta 2. Equation 1. Now moving ahead, we just rewrite with the help of geometry. You can write it down as you can see. Equation 2 comes from an identity from geometry. Exterior angle of a triangle is equal to the sum of two opposite angles inside the triangle, or you can say the interior angle. So with this we can write theta 1 or theta 2. We can find the value of theta 1 and theta 2. Putting it in the value of equation 1, or you can say Snell's law, theta 1 and theta 2, we can find the equation number 4. What is on the next page? So equation 4. After finding the equation 4, we can find the beta, gamma and alpha values. The moment we find the beta, gamma and alpha values, we can get mu2 upon v minus mu1 upon u equals to mu2 minus mu1 by r. So that is the famous relation. What that particular relation is this is your, you can say the relation between u, v and r for, or you can say the refraction at spherical surface is going to give you this relation. Is this clear till now? This one is clear or not? One page is going to be needed necessarily here. I don't know why don't they do that. Is this clear everyone here? Okay. So now if you can clear this thing. So understand in this way. Um, I can give you one picture to make things better. And there is a famous relation also. Okay, just a minute. This is visible. I mean, this is the handwritten of my note or my colleague note maybe. Is this clearly visible or not? This thing clearly visible, everyone? That is your lens maker formula. Lens maker formula. Clear? So as you can see, on the one surface, on the one spherical surface, we find this equation number 5. This equation number 5. On the second surface also we can find the same equation. Clear na? The above equation we can find the for the second equation also. So here we have NS, the medium of surface, or you can say other than medium of lens, NS, and that is the medium of, or you can say refractive index of lens is NL. So for surface 1, this is my first surface, this is my second surface. Clear? For the surface 1, this is my radius R1, this is my radius R2. For surface 1, I can write this relation as well. From the equation 5th, I can write this relation again, and that is N L upon V, or you can say V prime, because V prime is the small, you can say V prime is the virtual object for this second surface. V prime is virtual object, or you can say primary image for second surface. Or you can understand in this way also. V1 or V prime is image for first surface. For first surface. Understand in a clear way. Is this clear, everyone? Everyone. Everyone means everyone. Just clear, everyone, what I'm saying, what I'm writing here. As you can see, whenever this going to be scenario, there are two surface, combining two surface, we can make a lens in this way, right? The left hand side is one surface, right hand side is another surface. Both the surfaces is spherical in shape. So when I have this relation for spherical shape, or you can say V fraction for the spherical shape, mu2 divided by V minus mu1 divided by u, object distance, equals to mu2 minus mu1 divided by r. R is the radius of spherical surface. So I have spherical surfaces 2, and there are two spherical surfaces. So for first spherical surface NL, refractive index 2, right? Refractive index of medium or lens, minus V prime, image, minus NS divided by U, equals to NL minus NS divided by R1. This is my equation number 6. Or this is for surface 1. For surface 1, this is the scenario. Is this clear, everyone? This thing is clear or not? For surface 1, we have this equation number 6. In a same sense, for second surface, okay, for second surface, we have the reverse relation, which is, now the second medium is going to be NS and the first medium is going to be lens. So that is going to be NS divided by actual image, which is V, minus of NL divided by V prime, equals to ns minus nl divided by r. And this is your equation number 7. So this is clearly written over here. Now adding both the equations, you can say this equation and this equation. As you can see, this is NL positive, this is NL negative. This is divided by V prime, this is divided by V prime. So if I add both the equation, what I get? NS divided by V minus of NS divided by U. Is this clear, everyone? So adding equation 6 and 7, adding equation 6 and 7, what I get? This equation directly. Okay, adding equation 6 and 7, we can get equation number 8. This is clearly visible now, everyone, or should I increase the ratio? Because it is already written over there, so I don't need to write again and again. Good. So we get equation number 8. Now from equation number 8, we can take common ns. Clear? So ns, refractive index of other medium other than lens, 1 upon v minus 1 upon mu. And then again nl minus ns we can take common, and then in one side we have a ns minus nl, we have nl minus ns, so it is going to be converted into negative. So ns 1 upon v minus 1 upon mu, nl minus ns 1 upon r1 minus 1 upon r2. Clear? This is 1 by r2. Now same thing, divided whole equation with ns, so that is going to be this. Now we know this particular important case, if u is going to be infinite for any particular length, if, okay, we know this thing, if u is going to be infinity, then image we get v at focus. Clear? So put this thing in equation number 9, put this thing in equation number 9, which is 1 by v minus 1 by mu, 1 by v minus 1 by u equals to nl upon ns minus 1 by r1 minus 1 by r2. For this, 1 by f equals to this. So this is my lens maker formula, important one, equation number 10. Or this one is also okay. I don't need to write it again and again. This is clearly written over here and understood also. Okay. So this equation number 10 can represent the focal length of a lens also, if you know the refractive index of length and refractive index of other than, or you can say your surrounding. Clear? So here equation 10 represent lens maker formula, represents lens maker formula. Why it is known as lens maker formula? Means if we okay, wait, in the class 10 we already done this thing. Whenever there is a you can say any particular defect is going to be in eye, so we use lens of respective focal length, right? The focal length is going to be necessary, and according to the focal length we are going to learn in the next slides, we define the power. Clear na this thing? Power is 1 by focal length. We are going to find in this next slide. So the diopter, the power is going to be according to the this focal length. So how much focal length we require, that is dependent on the R1, R2 scenario, and dependent on the medium of length, or you can say refractive index of length and refractive index of surrounding. If in general there is more simply you can find it down, if surrounding is air, if surrounding, or in general surrounding is air, if surrounding is air, then what is going to be? Then ns is going to be 1. So equation number 10 can be rewrite 1 by f equals to n divided by 1, nothing, n minus 1, 1 upon r1 minus 1 by r2. So now you can see that automatically the equation number 11 is more simplistic way, which is totally dependent on the radius of the radius of two spherical surfaces for which we can make lens. Okay, and this is your equation number 11. Is this clear? N is the refractive index of a glass. R1, R2 is the refractive radius of curvature, or you can say for two spherical surfaces which can combine to make a lens. Or in general, that is going to be what? A slight difference, not equal. Is this clear? So that is very, very important. Clear with everyone? So this equation number 5 itself is an important thing. Or you can say very important. But from this equation number 5, we can define the lens maker formula also. And that is the thing. Nothing you need to do. Just if you know this equation number 5, so automatically you can find it down. Clear beta? Should I move ahead? Clear now everyone? Because I teach you on this page two important aspects, or you can say two important results or subtopics altogether. If you are having any particular, you can say query question, so you can ask me right now. Clear? Good. Now, refraction at a spherical surface, M1 is the refractive index of the medium in which the incident ray lies, M2, or you can say mu1, mu2. So let me write it down again, this thing, because we are following the mu1, mu2 scenario. This mu1 and that is your mu2. Okay. Mu1, mu2 is refractive index of medium in which the refracted ray lies. O is object, P is pole, C center of curvature, R is PC, radius of curvature. So although the formula 5 is obtained for a particular situation, it is applicable for all the conditions for refraction at a single spherical surface. And what is the formula number 5? Mu1 divided by V minus, okay, that is mu2. Mu2 divided by V minus mu1 divided by U equals to 1 by mu2 minus mu1 divided by R. That is equation number 5 na? Clear? So that is given for all. So this is my equation number. Why I separately write it down here? Because I give so much on the last page, so you don't going to be confused. Clear everyone now? So this is refraction at a spherical surfaces. So the sign convention, important one. Sign convention for radius of curvature. These are valid for all types of refracting surfaces. Either a concave, either a convex surface, or you can say, or either you can say convex, either concave or either plane spherical manner. In case of plane refracting surfaces, R is going to be infinite. So this relation is not going to fulfill. Clear? This is going to be fulfilled for only in which the radius is going to be something, or for a spherical surface. Is this clear, everyone? Okay. Why for a plane is the radius of what I am asking? The radius of curvature is going to be finite. Please, someone tell me about it. I mean, why should I write it down? R equals to infinite for a particular plane surface. Why? My question is this: why? Tell me why it is going to be. Why the radius is going to be infinite for plane surface? Very common sense. Tell me anyone. See, sometimes you need to use or apply very common, because U equals to V. Wow, beta, wow. Seriously, you can say that, but I am interested in geometry. UV is not going to matter here. See, this is your circle. This is sphere in 3D. Right? Is this clear? If I can say plane surface, so what is the meaning of plane surface? Plane surfaces. So this is having a, you can say, very, very, very large sphere with respect to object R tends to infinity. No, beta. Okay. What I'm drawing here, now you can see this. this small section and taken as a plane, isn't it? Can you right now? Clear I am saying? So for this particular small section, the radius of curvature is going to be more than, you can see, very, very large. And in physics, what is infinite? Because in mathematics, infinite we say that which is undefined value or 1 by 0. But in physics, we can define infinite. Suppose your eye length is going to be centimeter, right? And I put a particular lens which is going to be a radius of curvature of kilometer, that much large. Clear? And in, you can understand infinity in one more sense. In front of an ant, the height of a human is going to be infinite because it is very, very large, right? In the same sense, we are saying our eye's vision is going to be longest. In longest sense, it is going to be infinite, or you can say close point is going. The closest point is going to be 25 centimeter. After 25 centimeter, if you are going to read, so after a few minutes or after a few seconds, your eyes is going to be reframed, or you can say you're going to feel a pain a little bit in your eyes. So the closest point is 25 centimeter and the farthest point is infinite. What is the meaning of saying that? Being the height, being the length of a human, you can say 1.5 meter, we are able to see till few hundred kilometers. So that is the sense of infinity in physics. So for this particular length, suppose this particular length is 2 centimeter or 3 centimeter, and that is going to be very, very large. If it is going to be even 300 centimeters, so it is 100 times large. So but in general sense, it is going to be at least 10 to the power 6 order large, and we can say that infinite. That is the meaning of saying that. So simply with the help of even geometry, you can say that infinite, or you can say the plane surface is having a very, very large radius as compared to the surface even, or as compared to this plane, this length, because this particular plane is taken from a very, very large sphere which has a very, very large radius even. So when our radius is very, very large, we can make it for this, because it's supposed 3 cm. Again, it is, if it is 2 centimeter and the radius from a sphere which we take, this particular plane surface radius is, you can say, 1000 meter. So it is going to be very, very less. So in that sense, we can say radius is infinite. Clear it out. What is the meaning of infinite? So for the whale fish, or you can say that whale, the largest fish in the oceans, we human as a infinitely small, and for that, for us, the whale size is going to be infinitely large. Clear? In the same sense, for mosquito, for ants, for small insects, microorganisms, we are infinitely large, isn't it? Because if you put a small part of your finger, so that is going to be dry, either the mosquito, either the ant. Clear? So that is the meaning of infinity in physics at least. Okay, so these are valid for this. So then R is going to be radius. Why it is? The answer of why is because plane surface, taken from very, very large sphere. Okay, so if it is a very, very large sphere, so obviously the radius is going to be infinite. So then it is going to be very normal sense. Mu2 upon V minus mu1 upon U equals to 0. And then from this sense, we can say that object distance is image distance. So in 10th class, we tell you in a reverse, because if I am going to tell you this, even for you can say foundation, or you can say foundation course. What is the foundation course? In which we teach a little bit extra as compared to the CBSE thing only. So that is the real sense, and that is why the object distance is equal to the image distance in what? In plane surfaces. Whenever, even if a refraction is going to be, or whenever, even if a reflection is going to be. Clear? So that is the main thing. Now, u upon v equals to u1 by u2, because in plane mirror the both the medium are going to be equal, or DAC upon DAP. Here you can need to write it down, DAC DAP, that is u1 by u2. Okay, that is light from object from the left hand side and light of the object from the right hand side. So combining this R1 R1, we can make a lens. So this is your first question for the today's class. Find the position of the image formed and draw the appropriate ray diagram. You don't need to draw the ray diagram. R is given, U is given, okay, and this N2 is given, or you can say mu2 is given. Mu1 is obviously air, so you need to find the what image distance V using the formula. We already done that. Okay, do that. Quickly do that. After this, in this particular class, we are going to learn about lenses, different types of lenses. You can say principal, focus, and everything, and then power of a lenses and combination of a lenses. That's it. Calculate this, and then after that we can take a break. Or you can do one thing. Calculate in between the break. I need a break also. Okay, so there is a 5 to 10 minutes break. V equals to 90. Wait a minute, beta. I don't know. I need to check even. Yeah, we can be the 90 because that is very easy to understand. Yes, V equals to 90 centimeter, and that is going to be real. Okay, so that is the solution, and that is how we can draw the diagram. So on this page, take a 5 to 10 minutes, not more than 10 minutes break. After the break, we are going to do one more question, and then what is the length and everything. Okay. After this, in this particular lecture, not in, you can say something which is going to be a very time taken thing. Easy concept is going to be. Hello, 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 hello. Am I audible, beta, everyone? Am I visible also? Okay, so the next question related to the same thing, because for this particular concept you're going to fail or you're going to face the so many questions, and if you are lucky enough, so simple or direct question you're going to face for lens maker formula also, and if you are not going to be lucky enough, so one of the most complex or you can say hardest question you're going to face from the lens maker formula also. Okay, so the next question is almost same, just do that. Find out the position of image formed and draw the appropriate ray diagram. In this you can try to draw it also, because what happens if it is a theory question, so you need to draw in your final examination, right? So try to draw it, same similar question, everything is going to be same. N1 is given, object distance is given, N2 is given, R is given, you need to find the image. Clear? Just try to draw the diagram, because it is a concave surface. And if you don't able to try to at least draw the image. So just getting the image direction or just getting the image sign convention, you can get for which particular part you are going to get the image distance, or you can say you are going to get image. Clear? Do that and tell me the answer. The next thing after that, we are going to talk about lenses, different types of lenses. I'm not going to give you the proper definition like we already done in the class 10, but the basic thing we are going to revise, and then formula, or you can say power of a lens. Simple. And combination of a lenses, and if you silvering, and if you put particular lenses with some medium or in some different with some different distance d, so you can get it also. Meanwhile, I can see your, I mean, I can download also your CA classes also. Mm, just tell me and type the answer once you get it down. And in this month, at least we complete the optics part. So this is your this thing. There are 6 questions in C, and each one of the thing is easy one. You can get it done by easily. Still, the last one is like minus 6 centimeter. Exactly. So with the help of this minus 6 centimeter, using the same formula, nothing is needed to be changed. Solution. This one. mu2, or I am going to write n2n. n2 by v minus n1 by u equals to n2 n divided by r. Okay. So as you can see, negative. So obviously negative for which particular part, I'm not going to give you the proper drawing, but for this particular part we are talking about negative and positive sense, right? For this thing, this is taken as a origin. So if it is taken as a origin, so automatically you can feel and you can get it done. If it is a negative, I mean your image distance is going to be negative, so your image is going to be somewhere here. And for this, it is going to in this way. Okay. What is the scenario? Here this is going to be the incident ray, and if I draw a normal here, if I draw a normal here, just give me a minute. Okay, so that is going to be if it is the incident ray, so that is going to be tilted in this way a little bit, or if the proper we can. So it is not going to meet up after so long. So there is a imaginary line in the backward direction you can get, and there you get the image. Okay, so that is the scenario. Like in the previous page, we get in this way. So the moment it is going to touch with this eye, or you can say optical center, and this ray is going to be in the same direction, this one, and coming back to the same, because it is the light ray or the incident light ray passing through the center of curvature or passing through the pole, it is going to be undeviated. So one ray is this, another ray is this. So in this way we get image I at minus of 6 centimeter. And this one. N2 is this, N1 is this, U is this, R is this. And again R is why going to be taken as a negative sense, because it is a lens, or lens of which particular kind? Concave one. So the radius is going to be here. In this way you can get your sphere done. Clear na? So that is why we take R is a negative also. Clear this thing, everyone? See, this small points is going to take care by you guys and taken care by the student itself, because see, the moment you put R equals to positive, everything is going to be found. So either you, not remember, just understand this concept of positive, negative, and whenever there is a pole in this refraction system, in lens system, you need to draw a axis system. So obviously, every time you need to take care of this. Positive side is going, right hand side is going to be positive, upper side is going to be positive, left hand side is going to be negative, and downward. One important thing also, which particular kind of spherical surface, which particular kind of lens we are using. And for this particular reason itself, this particular radius of curvature of concave lens is going to be negative. Okay, and this radius of curvature or focal length for convex lens is going to be positive. So these are the small things you need to take in care. Now moving ahead, this is the lens. Everyone know what a lens is. A lens is you can say combination of two transparent medium which is going to give you the refraction, and with the help of which we are going to see the image, or we are going to create the image, which is going to bend the image, or not image, which is going to bend the rays, and we get the image at the correct position. Simple thing. Okay, so no one is going to ask the definition, but in a simple way what you can write it down, it is a combination of it is a combination of two transparent refraction, two transparent surfaces, in which one or both, in which, not this language is going to be correct, in which at least one surface, in which at least one of the surface is spherical, one of the surface is spherical. Wait, Clear, everyone? So if first of all the definition is not, no one is going to bother about it, no one is going to ask. But if you wanted to tell someone, if you wanted to uh, write the definition anywhere, so that is a perfect one. Okay. So as you can see, that is biconvex. Biconvex means, as bi means two, convex means both the surfaces are convex. It is equiconvex. Equiconvex means both the surfaces have equal radius and convex also. Plano-convex, simply one surface is plane and another surface is having a convex surface. Uh, Concavo-convex, one surface is a little bit concave and another surface is convex. This is look a little bit, you can say, mm, plane, but it is not in general plane. It is this a little bit inside. Okay, I mean, try to understand this thing. Uh, the second radius is going to be feel or seems like this plane surface, but it is not a plane surface. Clear, everyone? So this is different kinds. These are basically different different types of lenses. Clear, everyone? These are basically different types of lenses. Biconvex means both the surface are convex. Equiconvex means R1 equals to R2 equals to R1 equals to R2 equals to R. Plano-convex, one surface is going to be plane, so R1 is infinite, R2 is R in general. Okay, R1 is infinite, R2 is R. R2 goes to R. Then concave surface, R1 is convex surface, or you can say R2 is concave. Biconcave, you can say both the surface, again two surfaces are concave. Equiconcave, again here R1 equals to R2 equals to R, means both the surfaces are this concave surface. Plano concave and then convexo concave. So same thing, but in general we are talk about this second in great detail. Okay, and this one. Which one is this? First, second, third, fourth, fifth. Right, the down. Fifth. So these are two important things. Lens maker formula I already given to you guys. Okay, we can rewrite. Wait a minute. Just give me a second. So yeah, where I was. So in biconcave or biconvex or equiconcave or equiconvex surfaces, or you can say plane lenses, is going to be used in great detail. The ray diagram is going to be same. I don't generally edit. I just give you one note. But if you want to know the ray diagram, how to image can be formed with this, so let me know. Here it is. Tell me, do you want to? Because the whatever the image formation is going to be done by concave mirror, the same image formation you can get with the convex lens. Okay, and the image formation done with the convex mirror is going to be done with the same format, everything same in this convex lens. But in lens system we have a refraction, in the mirror system we have a reflection. Okay, let me write it down. Okay, for you guys, because that is not no one asked. Image formation with the lenses. Image formation with convex or concave lenses. Just wait for a while. Let me give it to you a diagram or a table. Okay, then I can tell you and then I can write this analogy, and you can correlate also. Okay, just a minute. See, no one is asking this, but still for you guys, I'm going to just a minute. Image formation for lens, and I think that is already done in previous classes also, but still it's okay. Okay, this one is the 6 cases. Just a minute. And 1 minute more. Okay, so as you can see, first of all, let me arrange these pictures. Is this clear, everyone? Is this visible? First of all, tell me this. And okay, let me make myself visible also for you guys. Visible now, everyone? Okay. So this is, now I just keep a little bit up, and that one keep a little bit up, and then I can redraw this line for you guys to give a partition. Yes, okay, now perfect. So this is for convex lens. For convex lens, okay, and this is for concave lens. And in a minute, you're going to get what I was saying. So now you can see there are 6 cases, as we have a 6 cases for concave mirror. Okay, let me write it in the same, analogous to concave mirror. Concave mirror image. Okay, and this one is analogous to convex mirror image formation. Clear? Just let me read this, and then we are going to this. Yes. So as you can see, there are 6 cases, and we have a 6 cases in concave mirror. At the very first stage, we are going to put an object very far away. You can say infinite. Then sliding towards the mirror, you can say beyond the center of curvature. Then we put at the center of curvature, and we get the image equal to the size of object, inverted real one. Then we put the object in between C and F, center of curvature and radius, or you can say focal length. Then we put the object in at the focal length, and we get the image at the infinity. Then we put the object for concave mirror I am talking right now, in between the pole of a mirror, or in between the pole or focus, and we get the virtual erect or large image. Clear? You remember these cases? The same analogy you can see here. Object at infinity, and you can get the image at focus. Case 2, object at beyond 2f. Here instead of writing c, because radius of curvature is nothing but twice of f. Okay, beyond 2f, we can get image real inverted in between focus and 2f. You can see that. This is your focus 2, this is your center 2 for second surface. Now, this is the third case. We can get we put the object at this particular point, center of curvature, 2f1 at c1. So we can get the same height image, real inverted at this particular point, c2. Clear this thing? In the same sense, you can see another cases also. Clear? Whereas in convex mirror, we have only two cases. Anywhere you can put the object, you can get the image at focus. Or if the incoming rays, or you can say if the incident rays are going to be from the focus, you can say infinite, so the image is going to be very, very small. The image is going to be very small or diminished, and we can get at focus. If we put a particular object anywhere, you can say in between the focus, or anywhere in between infinity or this particular point of optical center O. So we can get image diminished or small in between focus and optical center. So here we put the object, and here we get the small image. So these are the two cases. At infinity, the position of object is at infinity, position of image is at focus, and virtual, erect, and highly diminished. Means virtual, erect is going to be but very, very small. Between infinity at particular point, you can say at any particular point between infinity and O. O is the optical center. So you get, the position of images between F and O, focus and optical center, and virtual and erect and diminished. Not highly diminished, a little bit diminished. And that is the same case. You can find it in convex mirror image formation. Is this clear, everyone? Hello. Am I audible? Am I visible? Okay. Yeah. So the same cases you are going to find for concave mirror, for concave mirror image formation and for convex mirror image formation. So if you know any of the one case, or you can say for lens, so you can automatically get it done for mirror. If you know for the mirror, you can already get it done for lenses. Is this clear, everyone? I'm not going to draw, not even going to remind you what is the case for mirror. Go and check and revise yourself. Clear? There are very basic things, and there are not something you are going to, you can say, confuse in this. Never ever you are going to find any particular numerical question for JEE level for this diagram. So maybe if you are lucky enough, so you get assertion region question for any particular case, not more than that. Is this clear, everyone? Is this clear, beta? Should I move ahead? Clear na? Good. Now this is just a simple, you can say optical center what it is, and principal focus what it is, then lens what it is, and then this is the main thing, power of a lens. So let's revise this, what it is in general, everything, and then the main thing we are going to do. So this thing is done. So lens, optical center what it is, it is a point O for a given thin lens through which any ray passes undeviated. Optical center O is that particular point wherever any particular incident ray is going to be passes, so it is not going to deviate. Okay. Principal axis C1, C2 is a line passes through optical center and perpendicular to the lens. we are going to use this particular line to put an object and to find the object distance or image distance from the optical center. Is this clear, everyone? Is this clear, beta, everyone? Getting nothing? And for both, I mean same for both convex and concave lenses. Now principal focus, everyone know what is a principal focus? A lens has a two focal points. First focal point is an object. Is an object point on the principal axis corresponding to which the image is formed at infinity. As you can see, if you put any particular object here, so for this the image is going to be at infinity, and in the reverse case, if the parallel rays are going to be you can say coming from the infinite, so in reverse of this, if the parallel rays are going to be incident from the infinity, so we can get the image at focus. Or in this, if a object is situated at focus, so what it is going to be, the ray is going to be in this way and tilted, but they are going to meet. Why? That is the reverse case. It is not going to meet anywhere in this sense, in this scenario, because they are diverging away from each other, as you can see. Clear? So what we can feel, what we can see, that is going to meet at some particular point at infinity in the backward direction. Clear? In this way, in this way, and in this way. Okay, so that is our analogy. Clear, everyone? Now, whereas second focal point is an image point on the principal axis, that is the image point on the principal axis where you are going to get the corresponding to which object lies at infinity. Means if any object is situated at infinity, so we get the second focal point, which is the image point. Clear? In this way you can see for convex and concave lens, our first focal point is the point of object point when we put any particular object at the focus, either for a convex one, either for the concave one. So the rays are going to meet up at infinity. Simple as that. Or you can say that image is going to be at infinity. Here it is not written. Here it is clearly written over here. So when U is at focus, so that is one focal point, or is also known as object point. So V is going to be infinite for any particular lens. Clear? In the same sense, if object is situated at infinity, this object is situated at infinity, so automatically we can get at focus. Clear? For any particular case. Clear this thing? Now this is the power of a lens. Simply what a power means for you, or for in general sense. So power of a lens is the number, or you can say is the amount, how much the lens is going to deviate the ray after the refraction. Okay, it is the amount, or you can say power is defined, power of a lens first of all. Let me write it down. Power of a lens, power of a lens is defined, power of a lens is defined in such a way, which describe how much incident ray, how much incident ray is going to be deviated, by the lens. Clear? And the deviation is dependent on focal length. The more focal length, the more deviation is going to be, the more larger the you can say length is going to be. Why so? Because as we know, this f equals to 2r, or you can say radius of curvature is focal length by 2. Clear na? Is this clear? So the more focal length, the more deviation is going to be, or less. Tell me. Because power is going to be more for smaller focal length, not for larger. Tell me. Tell me why I'm asking this thing. See, more focal length gives you reverse thing. The more focal length, the more radius instead of this surface, or you can say spherical surface, the more plane surface we are going to get. So there is less deviation. You get na? In plane surface like this, we have a v equals to u. The more, that is the plane surface having radius r equals to infinity. So the lesser the focal length, the more curve you have, the more deviation you get. Clear it down. So that is why the less, in this sense, we directly say that power of a lens in air is PL inversely proportional to focal length. Why so? Because simply the moment R is going to infinity, or you can say focus is going to infinity also, then that particular surface, spherical surface, converted into plane surface. That particular surface is converted into plane surface, and we know this thing for plane surface using this again relation, using this relation of what the relation, V fraction for the spherical surface. I'm going to write N2 N1 because mu2 and this thing is going to be confused. N2 minus N1 by R. Okay. Yes. So this is the relation. The more you can say the radius is going to be infinity. So V and U is going to be equal. But in general sense, we need more deviation. So how we can get more deviation? Simple for this, R is going to be less. The R is less, more deviation we get. Clear? Deviation, R, radius curvature is less, or focal length is less, more deviation. More deviation with more deviation in between V and U for refraction, or from refraction, from refraction, from refraction at spherical surface. Spherical surfaces. Is this clear, beta? Clear na? So with this relation, as you can see, for plane surface we have a largest radius of curvature, we can say largest focal length, infinity. We don't get any particular deviation. So we need to make this deviation less. And that is why the less deviation, or you can say the more deviation, the less focal length, the more power. It is going to convert more and more, or it is going to deviate more and more. So using this relation, where FL is the always taken in SI unit. SI unit means in proper meter. So simply this thing, power of a lens in air is PL 1 by FL. It is going to be for meter. Okay. Where I can write? Wait, I can write here as well. Let me see. It is going to know. Simply it is already done in the class 10, but still for you guys, power of a lens P is nothing but 1 upon focal length of a lens, FL, you can say that. It is going to be in meter. If FL is going to be in meter, so it is this, and known as diopter. Okay. But instead of this, if we have, in general, we have focal length in centimeter. So that is going to be 100 upon FL diopter. And why so? Instead of it, we can say when this FL is in centimeter, or we can write in the same sense, same analogy, then FL, focal length of a lens, is in meter. Is this clear? So that is already we know from the previous class, from the 10th class. So that is why I not given to you guys, but still for again just a simple revision we can do that. Clear? And now we know this converging lens. What is the converging lens? Convex. So the focal length of a convex lens is positive and diverging lens is concave. Clear? So we know why it is going to be positive, negative, because the focal length of a converging lens, which is a convex lens, is going to be the positive. In the same sense, it is going to be negative for concave lens. And we already understood, we already know in the previous slides. So power of a lens in medium, refractive index of a medium divided by focal length of a medium. That is important one. Okay. Derivation and everything you don't necessary here. Now power of a mirror PM is minus of 1 by FM. Mirror we have a power also. How much it is going to give with the reflection. Convex mirror have positive, you can say convex mirror have a focal length positive, or you can say focal length of a convex mirror. Convex mirror is going to be positive. So with this negative sign, you can get the negative signs. And focal length of this concave mirror is going to be the negative, and due to this negative sign we can get the positive. Clear? Nothing more. We so everything everyone understood what a power is? Clear na everyone? Is this clear with everyone? You get what power is, how it is going to be related, why it is going to be related. So again the same main thing is the major important formula, this one. Clear? Now moving ahead, this is the combination of a lens, and in the combination of a lens the equivalent power is going to be direct the summation. Nothing you more need to do. If you have a power, you can say power P1 of lens L1 and power P2 of lens L2, and they are put all together. So with the sign convention, you can find it down. Instead of this, if I can do that also. Just give me a minute. Wait. Okay, let me make this first. Suppose what I'm trying to do here, this is your P naught, but as we draw this L A, or you can say this LC. LC is the length of concave lens, or you can say L3. Here L3 is concave lens, and automatically, and we know this, for concave lens, focal length for concave lens is going to be negative. So obviously power P naught is going to be negative. Or you can say negative of P naught directly. Okay. Negative of P naught. So now the equivalent is going to be negative of P naught. Is this clear, everyone? Clear na? So you need to follow the sign convention also. It's not like that just directly add it down. If there is a concave with convex, so the sign convention is going to be, if there is concave only, so negative sign you need to apply. If there is something like this, so you need to follow the sign convention. Clear? So that is simple general. Now moving ahead, combination of a lens if the diameter is going to be. So this is the second equation, or you can say important formula. Okay, P equivalent is going to be P1 P2 minus of D distance into P1 P2. Again, the derivation is not necessary, but it is important. Now, one of the more important formula you can get it down. The focal length of the equivalent mirror of a convex lens silvered at one side. So when on any particular side you silvered that. Silvered means you make a mirror of that. What is the meaning of saying that? If I draw or if I paint a silver color like this, so that surface now behave as a mirror. Okay, this surface 1 behave as a mirror. So if we are doing in this way, so the focal length of a equivalent mirror of a uh, convex lens is silvered at one side is power. Total power is power of a lens, power of a medium, and then power of a lens, 2 into power of a lens, and this 1 by total focal length, 1 by FL, 1 by FM, 1 by FL. Just putting this values and you can get this focal length. So this one is important also. Clear everyone? So there are 3 cases. That is another, not you can say that much, but if in any case you are going to get this, so there are 2 cases of combination of a lens. If the 2 lenses are situated at some distance d away from each other, so that is one equation, and if it is simply in a contact like this, so you can find it directly. Now this is your question on this particular plane, this power and everything. Do that and tell me the answer. Simple thing, radius of curvature of a surface of a plano convex lens. 20 centimeter, refractive index of a material is 1.5. Calculate the equivalent focal length of a lens if the surface is silvered. So you need to use this formula. R 4 mu minus 2. Okay. Yeah. Do that and tell me the answer. Do that, beta. Or okay, I am going to give you one hint because then you are able to do. Just a minute. For a plano concave thing, we have something like this. I mean, the question itself is in this way. Just a minute. Visible this one? Okay, so now as you can see, this is your question, and what we are going to do, R is given only, radius. Okay, and we know P actual power is 2PL plus PM, that is 2 mu minus, you need to use this formula. Use this formula to calculate the power. Okay, the power is given, and calculate the equivalent focal length. Okay, mu is given and everything is given. So first of all, get the power, and using the power equals to 1 by F, you can get the focal length. Do that now. Is this clear now? I already give you the answer. D1 is saying B. Oh my goodness. Please someone say A or C also. KBC खेल लेते हैं यहाँ पे. Isn't it? We can play the KBC. Neither D, neither B, neither A, neither C. Or maybe someone, I mean maybe everything. Did I give you directly this formula? After this you are asking D, B, C. Seriously. Okay, let me check. If it is a mirror thing, because it is the silvered part, right? So it is going to be minus of 1 by f. Or for minus of 1 by f, you need to apply minus sign. Clear? So use that. The answer is C. And now you see. Yes, it is clearly. That's why I will deliberately give you this diagram or this thing. P 2 power of lens plus Pn, this everything. But we have a power of for this mirror. We are talking for mirror. For plane surface, it is not going to bother about it. For plane surface, this mu2 by V minus mu1 by U is going to 0 na. So we are not taking care of this. We are taking care of this mirror now. And that is why the answer is C. Clear everyone? Clear? Okay. Try this one. Focal length directly. Magnification is given. Okay, let me. A lens placed between a candle. Okay. And a stable screen from a real triply magnified image of the candle on the screen. When the lens is shifted away from the candle by 0.8 meter without changing the position of the candle, a real image 1/3 the size of the candle is formed on the screen. Determine the focal length of the lens. Okay, there are two cases are given. Uh, there are wait a minute. There are two cases are given. In first case, the image is going to be what? Magnified or real inverted thrice. So using that, and in the second case, when you are going to shift, so the image is going to be 1 by 3 times. So with this relation, we can find x first, and then with the simple lens maker formula or this mirror formula, 1 by f equals to 1 by v minus 1 by u. Okay, you can find it down this thing. Or should I tell you this? Tell me. Okay, do one thing. You can see this answer because in see the answer is for first position m equals to v by u equals to minus of 3. The moment you change, so here in between the object is, you can say candle is, so 0.8 and the x is going to be thrice of x because the image is going to be, I mean this is the relation. Clear? So from here we can find x, and x is then object distance. So v is going to be thrice 1 by 2, or you can say image is thrice of object distance. So image is going to be 1.2, or object is going to be 0.4 meter, and the distance between them is, we are don't need to worry because once we get v and u we can find f. Is this clear everyone? This one. So here the focal length is going to be 0.3 meter. Is this clear, beta? Everyone, it is clear. Is this clear, everyone? Okay, if this thing is clear, so in this particular lecture, I mean this lecture is complete. We done important things, refraction at spherical surfaces. refraction by lens, power of a lens, combination of a thin lens and contact. So in this I added one more thing. You can say lens maker formula and the derivation of it. Lens maker formula and its derivation. Its derivation. Okay.